So how do you see my screen? Oh, wait a minute. Why this? Okay. Can you see the full screen
Yeah.
on your? Okay. And I believe students are fine with this slide. Anybody can answer me? So I believe it is okay.
Yeah.
Yes.
It is okay. It is okay for me. It is.
Yes. Okay. Okay. Chatting. Yes. Students answered me that screen is okay. Okay. Good. Time is 4:31 now, so but somehow we have not many students today. Why is it?
I can see 40 students at the moment.
It's supposed to be up 70, 80.
Okay. Okay.
지수 내 말 들려요? Somehow he's in trouble.
No, there is some box in your presentation, but probably not in mine. Yeah.
Yep.
Okay. If you escape and re-enter, probably this box will disappear. Anyhow, you didn't see any boxes in my presentation.
Well, I can see only you, little box on my right hand side.
No, it is in your presentation, but these are now is better. Now is better.
So now 51 students. Now it's better. I see a big gray box. Now several boxes. Now it's better. Okay. Now I don't know why. Oh, maybe I'm the.
Yeah, it is according
share.
When you move your mouse in your presentation.
The box is a chat window, raw processing when sharing the screen. Oh, I see. Okay. Now I understand. So I think it's better for us to start. Are you ready, Nino?
Yeah, I'm ready, of
okay.
course.
Okay, so welcome to our regular Thursday afternoon seminar. And again, we have a very wonderful presenter today. And let me please introduce Professor Dr. Antonino Arico of CNR ITAE, Institute of Transformation and Accumulation of Energy. and he is currently the director of the institute. Let me go briefly about his background. He got BS degree in industrial chemistry at somehow the European education system is a little bit different from us. That the degree of industrial chemistry belongs to the Faculty of Mathematics, Physics, and Natural Science of the University of Messina, Italy. So it is more like a College of Natural Sciences. And again, and Master in Chemical Process Technologies at the Faculty of Science of the University of Messina, Italy. And I didn't have information when he got his degrees. And also European Master is more like PhD in the States. And after his education, he started, 1993 is again, it could be a mistake. And he became a research scientist of CNR ITAE after got his degree. Then 2008, for 2 years as a visiting professor, Department of Engineering, University of Messina, a master's degree in materials science. Then 2014 to 2021, European Commission state representative members, SRG member representing Italy for the fuel cells and hydrogen joint undertaking. Then he continued as a EC state representative members, SRG member representing Italy, now for clean hydrogen joint undertaking. Then he became the director of the CNR ITAE Institute since 2020. And he got numerous awards. And firstly, in 2007, he was selected as a top Italian scientist in chemistry. And 2013, the top 20 top authors at the international level in the field of fuel cells for 10 years. So 10 years back to 2013. Then again, 2016, he was chosen as the 150 world most cited scholars in energy research by Elsevier Scopus. He has published about 370 papers, 8 patents, 2 books, and 10 book chapters. And his research interests are energy technologies with regard to fuel cells, electrolysis, electro-catalysis, and carbon dioxide recycling, batteries, solar cells, and materials science. And now please welcome Professor Nino Arico for his presentations.
Thank you.
It's all yours now.
Yeah. Thank you so much, Asuk, for your kind introduction. It is a great pleasure for me to be here today with you to discuss about the green hydrogen. I would just like to ask you if you can see my presentation. Eventually, you can reduce the zoom on the screen. Is that okay with my presentation?
Yes.
Okay, good. So Thank you, everybody, for attending this seminar. I will discuss about low temperature electrolysis as technology for green hydrogen production. I will start discussing some aspects regarding the green hydrogen economy, and we'll discuss more in detail materials involved in this technology, operation methods, technology, applications, and so on. I will try to stop after some slides in order to ask you if you have any comments or questions. So this is a seminar, so if there are some burning questions, you can also write in the chat. So let's go with this presentation, and starting from this slide. This slide is showing the concept of the green hydrogen economy. Can you see my mouse on the slide? Can you see my mouse moving on the slide? Yes, okay, nice. So regarding the green hydrogen economy, why hydrogen? Why we emphasize the use of hydrogen as a new energy vector? Hydrogen can effectively decarbonize, contribute to decarbonize the energy system, green hydrogen. When we speak about green hydrogen, we deal with the hydrogen produced using energy from renewable power sources like solar energy, as an example, photovoltaic or wind energy. Of course, we can also use biomasses, and we can use reforming of biogas, since this is a carbon neutral process. However, we will focus essentially on electrolysis that is fed by renewable electricity. So the combustion of hydrogen produces only pure water. So this means that there is no carbon dioxide emissions in the atmosphere. And the motivation is we have to address urgently significant issues like climate changes and of course, global warming. So we really need a step change in the use of energy. We need independence, energy independence, and energy security. And if we consider that combining renewable power sources with hydrogen, with renewable hydrogen, we can also achieve energy independence and energy security. Not only contributing to decarbonizing the energy system. So I'm showing here an electrolysis reactor that fed with renewable energy can produce hydrogen. Renewable hydrogen can be injected into the natural gas grid, and we can start already in decarbonizing the gas grid, because these gas can be used in residential applications, in combined heat and power systems. Hydrogen can be used, green hydrogen can be used as a feedstock chemical for the chemical industry. Of course, at the moment in the chemical industry, we use gray hydrogen. Gray hydrogen is a hydrogen produced from reforming of natural gas, from fossil fuels. We need, and with a significant release of CO2 emissions in the atmosphere. And you know, CO2 emissions are responsible for the global warming. So if we use green hydrogen in the industry, there are several processes that can benefit of this green hydrogen. Ammonia, synthesis of ammonia. Why ammonia is so important? Because most of the fertilizers are based on ammonia precursor. Steel making, metallurgy, we need high-grade heat, and this can be provided by hydrogen. Hydrogen can reduce the ferrite, the iron oxide, to produce steel. Hydrogen can be used in methanol, to synthesize methanol. Methanol is a precursor for polymers. hydrogen can be used in hydrogenation process in specialty chemicals. So we can have already a premium market for using green hydrogen. And we can also convert again green hydrogen using fuel cells for application in the automotive field, especially for heavy duty vehicles like buses, trains, and ships. But you of course could mention that also we have battery vehicles, but battery vehicles are not really able to manage with application in trains, in aviation, in ships, because of the energy density. The energy density of hydrogen is much higher, and the refueling time for hydrogen-based vehicles is much smaller. 3 minutes to have hydrogen refueling, for hydrogen refueling. Let's say half an hour for batteries. So for trains, for buses, for taxis, for ships, you know, hydrogen technologies are competitive with batteries. For city cars, of course, I would say that batteries have specific advantages. So this is the concept of the hydrogen economy. And now we can move to the next slide, where I can mention some other important aspects. Why hydrogen, why green hydrogen is so important. Green hydrogen can provide a seasonal storage. That means, especially in small islands, you can store energy for let's say 6 months or more. Hydrogen can be used for green balancing service, because you know that renewable power sources are intermittent, and some periods we have a surplus of renewable energy. That means hydrogen can convert the surplus of renewable energy into chemical energy that can be stored and used later when needed. Hydrogen can be used for methanation, can convert carbon dioxide into renewable fuels, renewable green fuels for mobility and for other applications. So there are several applications of hydrogen. That's the reason why in the European Union, and also I know that in countries like Korea, Japan, and so on, there is a national strategy on hydrogen, because hydrogen, also in US, in Australia, hydrogen is seen as the new energy vector that will contribute in decarbonizing the energy system. However, we need a technology to convert efficiently, a reliable technology to convert efficiently renewable energy, especially the surplus of renewable energy, into chemical energy, into hydrogen. And electrolysis is the best approach for that. So there are several electrolysis technologies. I'm focusing today on low temperature electrolysis. Of course, there is also high temperature electrolysis that has also good perspectives, but at the moment, low temperature electrolysis seems to have slightly better perspectives. We have 3 technologies for low temperature water splitting, electrochemical water splitting. Alkaline electrolysis, well-known, mature technology. PEM, polymer or proton exchange membrane electrolysis, and AM. AM is an ion exchange membrane electrolysis. The difference is that in the alkaline electrolysis, we use just a porous separator. I'm showing here this porous separator, and we have some recirculation of concentrated KOH, of caustic solution. So this is the approach used in the alkaline electrolysis. And we have at the cathode hydrogen evolution and migration of hydroxide ions to the anode, where we have oxygen evolution. In the PEM and AM electrolysis, we have zero gap cells, membrane-based. What does it mean, zero gap cells? That electrodes are coated onto the membrane. That means electrodes are stamped, coated onto the membrane. I will show some electron microscopy picture later, so you can see better how this approach is developed. PEM is dealing with protonic environment. We can get advantage of a high proton mobility. AM uses hydroxide ions that, of course, have lower mobility, but some other advantages that I will discuss later. Why membrane based electrolysis and zero gap cells? Because we have advantages in terms of smaller volume, lower ohmic drops, as an example, higher degree of gas purity. The membrane is a full density membrane. I will show some pictures later. And possibility to produce compressed gas, to increase the hydrogen pressure. We have also an increased level of safety because we don't have any recirculation of caustic electrolyte. We have just, let's say, good separation between oxygen and hydrogen evolved. Otherwise, we can reach the flammability limit. Now, in this slide, this is an overview of the materials that are used in low temperature PEM electrolysis technologies, alkaline, PEM, and AM. In the alkaline electrolysis, essentially we use non-critical raw materials. Of course, there is some cobalt, but cobalt can be replaced. But we use a nickel-based electrocatalysts. We use a diaphragm separator based on zirconia. And of course, this is and stainless steel for the bipolar plates. So this is a cheap technology. The active area can be several square meters. So this is a really big reactors. The drawback is the low operating current density. And, you know, the low hydrogen purity. In the case of PEM, proton exchange membrane electrolysis, we have precious metals, platinum, ruthenium, iridium. We have perfluorosulfonic membranes that are also expensive. But how to compete with alkaline? We can operate on the current density. Using this technology, we have a low ohmic drop because of the good proton mobility, and we can operate at the high current density, in this case, 2 amperes square centimeter. So operating at high current density, we increase the production capacity because you know very well the Faraday law. The Faraday law correlate current with reaction rate. According to the Faraday law, the current density is corresponding to the reaction rate. So if we increase the reaction rate, we increase the production capacity and we can minimize precious metal electrocatalysts. Other relevant advantages are high purity for hydrogen, good dynamic behavior, high pressure. So there is a strong effort on developing PEM electrolysis. And we have DAM. DAM is a compromise, is a trade-off between alkaline and PEM, because we have a membrane that is similar to the PEM, but this membrane is an ion conducting membrane, conducting hydroxide ions. We use non-critical raw materials like in the alkaline. We can increase the current density, not at the same level of PEM, because the mobility of hydroxide is not the same of the mobility of protons, but we can really approach practical current density. So we can minimize materials. We can combine advantages of alkaline and PEM, also in terms of gas purity and high pressure. So just to summarize this part, polymer electrolyte membrane have advantages versus alkaline in terms of much higher operating current density, compact system, higher gas purity, high pressure, increases the level of safety. So we have a cheap technology on one side, a another technology that is not cheap, but I would say cost effective, because we have other advantages. And we needed to develop both technologies in parallel, because we don't know which strategies should be implemented in the future. Now, let's have a look to the core part of these technologies, especially the polymer membrane electrolyte. The core part is based on the so-called membrane electrode assembly. This is an MEA that has been dismantled after 3,000 hours operation. You can still see that after 3,000 hours operation, you have the electrodes layer, the bright layer, sticking to the dark layer that is the membrane. This is the electrode, this is the membrane, the electrocatalyst, this is the membrane, this is the electrocatalyst, this is the membrane. So the dark part in between is the membrane, full density polymer membrane. The bright part is the electrocatalyst. And using this concept, we have very low ohmic drops. We can reach extremely high current density. As example, we can reach 6 amperes square centimeter at a cell voltage lower than 2 volts. And using this extremely high reaction rate, we can really minimize the use of critical raw materials. We can increase the production capacity. Now, we use a polarization curve to understand the performance and the efficiency of this device, of this electrochemical reactor. So, of course, current density is related to the production capacity. Potential or cell voltage is related to the voltage efficiency, to the efficiency. So if we decrease the cell voltage, we can increase efficiency. Efficiency increases if we decrease the operating voltage. Of course, we cannot decrease the operating voltage below 1.4, 1.48 volts at ambient temperature, because this is the thermoneutral potential. This is limited by thermodynamics, so we cannot really achieve something that is not permitted by thermodynamics. And the limitation, thermodynamic limitation, is 1.4 volts about. But we can really decrease the cell voltage to approach this value. And we also need to assess Faradaic efficiency. So if the current is exactly corresponding to the desired, to the hydrogen production according to the Faraday law, we can measure the flow rate of hydrogen. We can measure the purity using gas chromatographic analysis. Now, let's move to the next slide. In the next slide, I can show you 2 aspects. First, on the left, you can see several polarization curves at different temperatures, but at different catalyst loadings. So you can see that the efficiency indicated by the arrow is increasing by increasing the catalyst loading. But since we use precious metals, we need to achieve a compromise. The efficiency is also increased by increasing the operating temperature. And here we have a limitation, because we cannot exceed 90 degrees Celsius, otherwise water will be boiling. Water is boiling, and of course the membrane will dry. So we can, and also to have good stability, we need some temperature in between. And so temperature, catalyst loading are relevant, let's say, parameters affecting the efficiency of the system and the operating current density. We, of course, need to understand which is the rate determining step in these processes, and we use electrochemical impedance spectroscopy. This electrochemical impedance spectroscopy is, of course, the best representation is the so-called Nyquist plot, where we can see the first high frequency point is the series resistance. The low frequency point is the, let's say, total resistance. The extension of the semicircle is related to the polarization resistance. The series resistance is the ohmic resistance. So we can understand ohmic resistance, polarization resistance. We can understand the contribution of membrane, contribution of electrons. We can understand how much is the total resistance. In order to achieve a higher performance, we need to decrease this total resistance. How? As an example, by increasing temperature or by increasing catalyst loading. So the electrochemical diagnostics allows to understand which aspect we need to improve to achieve better efficiency. And of course, this can be, these results can be plotted as function of temperature. In this case, we can see that membrane is dominant compared to anode and cathode contributions in terms of resistance. Now, let's move a little bit to the materials aspects. I know that some of you, Ashok mentioned that some of you are involved in material science. Of course, materials are extremely important in this field because the core part of this technology is made by functional materials. For functional materials, we intend electrocatalysts and membrane. When we started, I will say, 15 years ago to study electrolysis, we were focusing on nano-sized amorphous iridium oxide nanoparticle for the anode. And after several years, we realized that the crystallographic structure plays a relevant role. That means intrinsic activity is extremely important, and we need specific crystallographic orientation. As an example, in this case, we have a solid oxide solution between iridium oxide and ruthenium oxide. What about the membrane? Nafion is used widely through the world. Nafion is produced by, let's say, DuPont. And this is multinational, but we have understood that this was not the perfect membrane for PEM electrolysis. And we have tried to implement a new membrane produced by Solvay, a short-side chain membrane. This is a perfluorosulfonic membrane. Why? Because we need the fluorine because of the electron withdrawing effect. So we have electrons going through this chain, side chain. So this means better, let's say, better separation between oxygen and protons. Oxygen remains anchored and protons that will move. Better dissociation. But Aquivion has also high glass transition temperature, has a good crystallinity, so it is more robust than Nafion. And this was shown in several papers that we published together with Solvay in the past years, showing a better, lower series resistance, better conductivity, but also better interface with the electrodes. And our colleagues at ITAE Power in UK, they have shown that using a parallel experiment, that means two plants running in parallel, using the same water, the same feed water, in order to avoid any, let's say, interference from other effects. So the Aquivion membrane, the short side chain membrane, Aquivion membrane shows a much better efficiency. 87% voltage efficiency compared to 83% voltage efficiency of Nafion. And now just jump into the technology. We have here the renewable power source. This is the Electrolyte project. It was a project that I had the honor to coordinate some time ago, several years ago, using a small wind turbine, producing such intermittent power profile, because wind is not stable. Wind is, let's say, fluctuating. Wind energy is fluctuating. And using this reactor, we were able to demonstrate extremely high efficiency and good dynamic behavior. And just remaining on the technology, in a subsequent project, HPEM to gas, we combined enhanced materials, membrane and electrocatalysts into this MEA. You can see the MEA. This is the electron microscopy picture of the MEA. This is the electrodes and the membrane between. This has been installed into these stacks. Each stack is something like 40 cells, something like that. And these, of course, can be installed in a system. At the end of the day, we need a system to address the real life application. But it is important to keep high current density at the cutting edge efficiency, low energy consumption, high durability, that means low degradation rate. And all these aspects can make low the capital costs of these systems. Coming back to the materials, so I'm showing you something related to the materials, something related to the technology, in order to emphasize that the key advantage that we can achieve on the materials reflect on a much better technology, much more efficient technology. I have mentioned that the crystallographic structure plays an important role, especially for the anode, for the oxygen evolution reaction, that is a rate determining step. We need small particle size, that means small particles, but still at the same time crystalline. You can see this is a dimension of 5 nanometers. You can see here iridium atoms in a squared particle. This is a really an atomic image of the structure that we want to develop and have in the catalyst, that is offering a well-defined crystallographic orientation 110 that provides the best electrochemical activity, the best catalytic activity. But the real situation, this is really a, let's say, a specific situation. Usually you have a mixture of several particles, and also you want to have good distribution of the elements. As an example, iridium, in this case, ruthenium is inside the particle. Iridium is on the surface of the particle in order to achieve good electrochemical activity and also good stability. Now, of course, the structure of the catalyst is extremely important, but I have also mentioned the effect of the catalyst loading. If we reduce the catalyst loading, we have some decrease of efficiency. You can see some, let's say, higher cell voltage, but this is really not much. What is really more evident is the increase of degradation rate. If we reduce significantly the catalyst loading, we have a strong increase in degradation rate. And we have observed that there is a relationship between degradation rate and the turnover frequency. Turnover frequency is linked to the operating current density and to the reciprocal of catalyst loading. So if we decrease the catalyst loading and increase the current density, we have a higher degradation rate. This means that there is still a long way to go in order to develop stable and highly performing electrocatalysts. So I think I have provided some overview about the technology, and I think we can have some initial questions or comments. So I would like to ask you if you have some initial, some burning questions or comments. Oh, any questions or comments? So is everything clear with you? Okay, so we'll postpone questions and comments at the end. Can you hear my voice very well, or you have difficulties in hearing my voice? Yeah.
Well, we hear you well.
Oh. Okay, good. So you can hear well from me. Perfect. So let's move on. Let's move on. Now, coming back to the membrane, we have discussed a little bit about catalysts, but now let's come back on membrane. So how to assess the properties of the membrane? We, of course, measure proton conductivity as function of relative humidity, and we also measure the so-called dimensional swelling, because we need to have a stable membrane. And this is for the Aquivion. And of course, you have different approaches for preparing a membrane. You can have cast or extruded membranes. Here are some pictures of the MEA, and you can see that not much different in polarization resistance, and of course similar variation of total resistance with let's say temperature. But regarding stability, we can clearly see that the cast membrane is better performing than the extruded membrane, lower cell voltage at the same current density. And with the cast membrane, we can reach a current density of something like 4 ampere square centimeter. But there is another aspect to consider. Another important aspect to consider is dealing with, hydrogen crossover. I have mentioned that membrane is a full density, but in principle, there is a possibility, since there are some water channels inside the membrane, you can still have some gas crossover. So in this case, regarding the gas crossover, the concentration of hydrogen in the oxygen stream becomes lower when you increase the current density, because you have a lot of oxygen evolution, you have a lot of oxygen evolving that will dilute the hydrogen permeating through the membrane. But it can be critical at low current density. Critical because at low current density, we can achieve the flammability limit. The flammability limit is 4% hydrogen in oxygen. This must be avoided. The safe operating range is below 2% of hydrogen in oxygen. And this is really an important aspect to address. How we have tried to solve this issue in our PEM technology? We have introduced the concept of the recombination catalyst. The recombination catalyst is a platinum-based catalyst that can be mixed with iridium oxide at the anode, or you can have a dual layer. So when this is the membrane, so when hydrogen is permeated through the membrane, the first layer that encounters passes is the platinum-based layer. Here, hydrogen can recombine with the evolved oxygen, or can be electrochemical oxidized. So using this approach, we can achieve high differential pressure operation. That means pressurized hydrogen, non-pressurized oxygen. Why pressurized hydrogen? Because we need to have reduced the energy consumption in the downstream compression of hydrogen. So this is a clear example. Using this recombination catalyst and using a Bayer MEA, we have a much lower concentration of hydrogen in the oxygen stream at the anode in the presence of the recombination catalyst. And yeah, this is the dual layer that is perfectly operating for recombining this hydrogen. And you will be interested in understanding if using this recombination catalyst, we have a still good durability. And this slide shows that these are tests of 3 3,500 hours, something like 4 months. In this test, of course, we have some startup shutdown in between because we have some laboratory maintenance and so on. But what you can clearly see is that using the recombination catalyst, we have also better durability. And of course, we use a lot in our laboratory, a lot of post-operation analysis to understand membrane thinning, to understand, let's say, changes in morphology, to understand if degradation is related to these aspects. Now, again, I jump into this technology. What is really important for us is that all these concepts are validated in a practical stack. You can see here a practical reactor. This is a, let's say, something like 70 cells stack, a PEM electrolysis stack. You have 70 cells integrated. So the black, part you can see are the bipolar plates, because the MEA is extremely thin, is less than ½ millimeter thick, but the bipolar plates are a few millimeter thick. So this is, in this case, we have used, this has been developed by our colleague at ITM Power in UK in the framework of the project HPM to gas. And in this case, we use hydraulic compression. You can see that there are no tie rods here. This is a hydraulic compression in order to have a compression that is homogeneous through the cell. Using this approach, using the enhanced materials, we have achieved extremely high performance at cutting edge efficiency. Now, of course, as I mentioned at the very beginning, our technology, the electrolysis technology, is important to address the surplus, to convert the surplus of renewable electricity. This is this plot. This is a, let's say, recording of the surplus of renewable electricity in wintertime in northwest of Germany, in Emden, in the city of Emden. We can here see that we have a significant surplus of renewable electricity. This surplus cannot be fed into the grid. So the grid operator has to cut this surplus of electricity if, of course, there is no need for this electricity. But we can store this surplus into hydrogen and use later, as an example, in summertime. This wind energy. So this is essentially surplus in January, February, December, of course. And here and in Emden, we have installed this system that you can see the stack installed into the system. And the system was located in a plant where you have a natural gas uptake station. So using the wind energy, this is a 200 kilowatt system. Using the surplus of wind energy. This is a proof of concept, of course. This was converted into hydrogen and fed into the natural gas grid. This is a picture of our kickoff of our inauguration of the plant. You can clearly see it is a very compact electrolysis system. So we don't need for cumbersome plants. We need, if we can operate at high current density, we just need very compact systems. And this is a proof how the technology is validated in the real life. Of course, we have also observed that during the operation of the system that degradation under duty cycles was a little bit higher than under steady state. And of course, degradation means a loss of efficiency with time. And this is essentially related to the electrode behavior, much less to the membrane, really less to the membrane. And these are, as an example, MEAs dismantled after a prolonged durability test, showing very little membrane thinning. Also, the catalyst morphology is not changing much. What is really changing is the electronic properties, the oxidation state of the anode catalyst, and some ruthenium dissolution. So We can see here by XPS analysis that we have a change in the oxidation state, but also loss of ruthenium with time. And this is, you know, the drawback that has caused a loss in this diagram, a loss of efficiency, an increase of the cell voltage. So this is clearly represented in this table, where you can see change of the atomic percent of ruthenium. Ruthenium is providing extra activity to iridium oxide, and this is an important aspect, and also changing the oxidation state. So this is also part of the material science studies that we have carried out around this technology. So not only validating the technology in the real life, under real life operation, but also trying to understand which are the drawbacks that can really should be overcome to provide better perspective for the future. And now discussing about the future, the extruded membrane, the membrane that uses this polymer net, this PTFE polymer net inside, in the core, and the ionomer on the surface is the best approach for the future, because we have a robust polymer inside that can allow operation at extremely high pressures, like 100 bars would be possible using this approach. And we can see that using this approach, we have also good, nice performance, better than the extruded membrane, as you can see from the shift of the series resistance in the AC impedance spectroscopy curves. And durability is also another important aspect, because usually to estimate the durability, you need, in this case, because degradation rate is very low. So to make an estimation of the degradation rate, you need to operate your cells for about 4 months, 5 months, 6 months. So you can really understand durability, you can really make an estimation of the degradation rate. And you can see that the reinforced membranes is characterized by better efficiency, but also low degradation rate. You know, in this case, we had a water supply issue, and you can see the efficiency was decreasing immediately, but after solving the problem, we have achieved a nice efficiency. Also, using extruded, using reinforced membranes, we have a nice interface with the electrocatalysts. As you can see from these cyclic voltammetry studies, you can see the nice cyclic voltammetry from the cathode, and also nice cyclic voltammetry for the anode. The cathode is not changing much after 3,500 hours operation. Some changes are observed at the anode. You can see decrease of the capacitance. This is also another important diagnostic, in situ diagnostic tool to understand also variations, and also ex situ SEM, ADX, and XPS are really important. I would like to mention an important aspect, that is the cost of precious metals. This has dramatically increased in the last years. So of course, this is really, you know, a big challenge for the PEM electrolysis, because the cost of iridium, ruthenium, and platinum is dramatically increasing. And to address this aspect, we are now moving little by little to the AM electrolysis technology that is similar to the PEM, but since operates in the alkaline environment, doesn't use any critical raw material. And as shown in this slide, we can see that the anion exchange membranes, we have a membrane that could be reinforced, we have a high differential pressure, we have essentially nickel iron and nickel manganese oxides as electrodes, and we have steel, not titanium. So we have cheap materials in this case. And of course, we have a lower conductivity for the anion exchange membrane compared to PEM, 50 millisiemens compared to 200. That means lower performance. But still, what I want to show is that we have, using, in the case of AM electrolysis, non-critical raw materials like nickel, nickel iron oxide, we can really achieve a good efficiency and a good durability. In this case, a nice durability because we have a decrease of efficiency, decrease of cell voltage with time. That means increase of efficiency. And this is a small prototype, 100 square centimeter. Of course, this is the new frontier in the electrolysis technology. So, but still, 100 square centimeter is nice to really study the performance. And of course, we have a roadmap to improve the anode electrocatalyst and also to improve the cathode electrocatalyst. The anode electrocatalyst is unsupported, small particle size. The cathode electrocatalyst is supported on carbon. We cannot use carbon at the anode. Carbon will be oxidized and burned to CO2. And also in this case, we have good durability. That means these are tested to 2,000 hours, but some new drawback, that is the reversible losses. You can see some reversible losses when you have a startup, shutdown, you can see some reversible losses. So dynamic behavior of IM electrolysis is not as good as PEM electrolysis. And we also need to recirculate some KOH because, of course, to enhance a little bit the conductivity. 1 molar KOH. When we decrease it to 0.1 molar KOH, you can see there is a loss of efficiency and increase of cell voltage. This is another important aspect. So you will probably you will be interested in understanding how the AM technology compares to the PEM technology. The PEM technology is very efficient, low operating cell voltage at 2 ampere square centimeter. In the case of AM, you have an increase of cell voltage. So the gap that we have at a practical current density of 2 ampere square centimeter is something like 300 millivolts. That is really, at the moment, a significant gap, a significant drawback, and is essentially related to the polarization resistance, to the electrocatalyst behavior. So there is still a long way to go to bring the performance of the AM technology close to PEM technology. But using AM, we don't have any critical raw materials. We don't have precious metal electrocatalysts. We have hydrocarbon membranes instead of perfluorinated membranes. We use steel. We use stainless steel. We don't use titanium in this case. So we have significant advantages, but still efficiency gap. And this is my last slide regarding the photoelectrolysis. I would like to mention that it is probably low technology readiness level technology. Probably in 20 years we can see some practical applications. But it is very important because you have a direct conversion of the solar energy into hydrogen. And this is a nice concept, the so-called tandem cell, using the AM membrane, the anion exchange membrane, in between a photoanode and a photocathode. This is a transparent membrane. So the photoanode, that is iron oxide, is absorbing the low wavelengths, so the high energy part of the solar spectrum. The low energy is passing through the membrane, the higher wavelengths. This is a 2 EV gap. This is a 1.2 EV gap. So a larger wavelengths pass through this semiconductor. That means lower energy pass through this semiconductor through the membrane, reaching the photocathode, and you have a good matching with the solar spectrum. You can convert most of the solar energy. And this on-off polarization curve, it is a photodiode representation model. You can see something like 5 milliampere square centimeter at practical cell voltages. And you know, in a photovoltaic cell, you have 20 milliampere square centimeter. So we are not really far from the photovoltaic, but still we need some further development. This is just a small prototype that we've developed in the project. So I would like to conclude with this slide, and I thank you for your kind attention, and also my thanks to Professor Asok Kim for giving me this opportunity to discuss with you these recent advances on hydrogen technology. So thank you so much. I'm of course available for questions, comments, for curiosities. So please feel you free to ask any question. It is not important if you are not expert of the field. Any curiosity or questions you would like to ask, please go ahead. Thank you.
Well, thank you, Nino, for your wonderful presentation. And now, as he mentioned, the session is open for questions or comments. I'll ask a student first. Either you can directly address your questions or send your questions through chatting panel.
Okay, I see a question on the chat, and the question is, I have a simple question about electrochemical impedance spectroscopy for the determination. Oh, this question is from Kamal. I have a simple question about the electrochemical impedance spectroscopy for the determination of the rate determining step. As we also observe the hydrogen evolution during CO2 reduction, by using a impedance spectroscopy, can we calculate the rate determining step for hydrogen evolution reaction coming from water electrolysis and the hydrogen evolution reaction coming from water reduction, which competes with CO2 reduction? Does IS give different results from these rate determining steps for these two different systems? Oh, this is really an interesting question. Thank you for this question. Of course, I understand that some of you are interested in co-electrolysis. Co-electrolysis is a reduction of CO2 and water, and to get alcohols as an example. But we have a parallel step that is really regarding hydrogen evolution. Of course, from a single Nyquist plot, we cannot. We can say something, but we cannot say much because we need a comparison. What is really important is to make a impedance spectroscopy experiments in the absence of CO2, as an example, by feeding in nitrogen, and in presence of CO2. Because you can see change in polarization resistance. You can understand that the change in polarization resistance is associated to the absorption of CO2 on the electrodes, contributing to the rate determining step. In my experience with the co-electrolysis of CO2 and water, when we feed the CO2, we have a dramatic increase of polarization resistance. That means CO2 reduction becomes the rate determining step. But this is on copper-based electrocatalysts. And of course, by simulation, by modeling, we can associate this polarization resistance to reaction kinetics constants. So this could be possible. So it is not an easy task, but I would suggest first making comparison under different operating conditions. With CO2, without CO2, low temperature, high temperature, different operating voltages. So to get a picture, first a qualitative pictures, and after by equivalent circuit simulation, determine the the specific parameters, and from the, let's say, specific resistances, and from a specific resistance, the rate constants. So, is there any other question? You can also ask, you can also open your microphone and ask, please, or if you want, you can still use the chat. Okay, I see another question coming. This is from, let me see, this is from Yang Yun He, and he asks, why is the major reason why AMST is still on R&D stage, membrane or catalyst? What types of membranes are used for AM, cationic like amine or imidazole based? What is the major issue? Hydroxide conductivity or durability? This is also a very interesting question. So why AM is still, let's say, under development? Why we don't have already plants running? The reason is that AM membranes, anion exchange membranes, have been introduced later compared to proton exchange membranes. Nafion is well known from the 50s or 60s. So Nafion is a membrane, and Nafion that is already known from more than 50 or 60 years. AM membranes are essentially based on quaternary ammonium functional groups, quaternary ammonium, but also imidazole. Most of the membranes are quaternary ammonium functional groups. So we have nitrogen functionalities, and we have hydroxide to provide charge neutrality. So these membranes are not so stable or not so robust like Nafion. Nafion is extremely robust. Also Aquivion, of course, but AM membranes suffer of poor durability. At the moment, we need to run experiments only at 50 degrees Celsius, because at higher temperature, we suffer a lot from durability. So this is an issue. Another issue is dealing with the electrocatalysts, because passing from PEM to AM, we don't use any precious metal electrocatalysts in AM. It is really not needed using precious metal electrocatalysts in the alkaline environment, because we can save a lot of money, but still we lost some electrocatalytic activity. And these electrocatalysts have not been yet improved, because we needed to improve morphology, structure. The research on AM has started something like 5-10 years ago. The research on PEM is really 40 years old. The research on alkaline is 1 century old. So there is a long way to go on AM membranes. We need to, on AM technology, we need to improve membranes and electrocatalysis. You are welcome. You are welcome. So, any other question?
Well, Nino, I have one simple question. And
please.
Yeah, when you're talking about the tandem cell concept,
yeah,
for hydrogen generations with solar cell, and of course the idea is very interesting and has been utilized for many years back. And is it necessary to consider the light transmission through membrane?
Yeah. Thank you for this question. Yeah, this is very important. We in this tandem concept, we need transparent membranes. That means membrane transparent in the specific wavelength range.
Yes, yes,
because,
exactly.
Because we, from this picture above, that we can absorb until 600 nanometer, all wavelengths until 600 nanometers are absorbed. From ultraviolet under 600 nanometers are absorbed by the iron oxide.
Yes,
that is the
yes.
high energy gap semiconductor. So the wavelengths that are close to the infrared, that have lower energy but can pass the first semiconductor, should also pass the membrane. So the membrane should be transparent in that field. So we have done a lot of spectrophotometric analysis of the membrane and selected the membrane that is transparent in the specific, in the useful wavelength range to reach the copper oxide. So unfortunately, I presented just a single slide, but we have published so many papers. If you are interested to this topic, you can have a look to all these papers published, and you can really see that at the end of the day, we have the photo response as the sum of the contribution of anode and cathode. I hope I have answered your question.
Yeah, yes. So it is very important, I think, to find the membrane which is transparent to a specific visible light in order to utilize some part of the spectrum, the light energy to produce hydrogen.
Yeah,
yes.
Of course.
Yes. Okay. Are there any other questions? Comments?
Curiosities?
And I'll give you 5 more seconds before I close the seminar. And would you please terminate the screen sharing from your side so that I can use mine? Okay, thank you. And where is it? Yes. And again, I really appreciate for Nino Arico for his participation to our regular seminar this time. And I will announce next week's seminar. And another very important person in battery research, Professor Doron Orbach of Bar-Ilan University of Israel. And he's going to talk on rechargeable batteries for electromobility, challenges, and reality. And I would like to point out that next week's seminar will start from 5 p.m., not 4:30, so 30 minutes after our regular seminar time. So please remember that next week's seminar starts at 5 p.m. 5 p.m., not 4:30, 5 p.m. Then another one is, of course, this seminar report is due noon on June 23rd. Noon on June 23rd. That's a very important deadline for students. Well, this is it. And thank you, Nino, for your very wonderful presentation. And I also would like to thank all students to attend the seminar. I have noticed that we had 64 at one time, now 61. So we are going to take pictures. So please say cheese for next 10 seconds so that our staff can take picture. Say cheese, everybody. Okay. Okay, I will finish the seminar today. And again, thank you, Nino, and hope to see you sometime. Bye.
Thank you.
Bye.
Thank you. Bye. Thank you.
Bye,
Bye.
everybody.
Bye. Bye. Thank you. Thank
Bye.
you to everybody. Bye.
Yes.
Bye. Bye.
I'll see you next week. Bye.